Okay, please start.
Okay. Okay. So thanks. So good morning, good afternoon, and maybe good evening to some of you, and welcome to my talk. And today I'm going to talk about the Renyi entropy rate of stationary ergodic processes. And this is a joint work with Yonglong Li, Li Xu, and Guangyue Han. So here is a summary of my talk. So basically, my talk will be divided into two parts. So the first part, we will consider the Renyi entropy rate of a special class of random processes. And this special class of random process will contain hidden macroprocesses as a special case. That's the reason we focus on this kind of random processes. And in this part, we first prove the existence of the Renyi entropy rate for this class of random processes. And we also give a explicit convergence rate. And secondly, we will talk about we want to accelerate the convergence rate to the Renyi entropy rate. So we use another sequence to approximate the original sequence, which is called, and the approximating sequence is called the Markov approximation. And we prove that by using this new sequence to approximate the original sequence, then the Renyi entropy rate of the Markov approximation will converge exponentially to the Renyi entropy rate of the original process. And then the second part of my talk will be focusing on whether, somewhat continuity of the Renyi entropy rate. So in this part, we will show that the Renyi entropy rate may not converge to the Shannon entropy rate for some ergodic processes. And the method we use is the so-called cutting and stacking method, which is a very more or less popular method in ergodic theory. And after introducing that method, I will give a construction of our counterexample. And after that, we will give the property of the process we construct. And you will see from the property that the Renyi entropy rate of the process exists, but it will not convert to the Shannon entropy rate. Okay, so let's move to the first section, which is the Renyi entropy rate of the special class of random processes. So let me first give you the definition of the Renyi entropy. So if you have a random vector, Z1n, the alpha order Renyi entropy is defined as when alpha equals to 1, it is just defined as the Shannon entropy. And when alpha doesn't equal to 1, then it is defined as the log of the summation of the alpha's power of all the probabilities of the realization D1n and normalized by the constant 1 minus alpha. So because at a special point alpha equals to 1, it is defined as the Shannon entropy. So this Renyi entropy can be viewed as a generalization of the Shannon entropy. And of course, using the hospital rule, you can easily show that this definition is continuous in the sense that as alpha approaches 1, then this Renyi entropy will approach the Shannon entropy. And then for random process, we can define the Renyi entropy rate similarly as how we define the Shannon entropy rate from the Shannon entropy of a random vector. So basically, we define the alpha order Renyi entropy rate for process as the limit of the average version of the Shannon entropy, and whenever the limit exists. So here are the two questions we care about. So we know that for Shannon entropy rate, it always exists for stationary process, for any stationary process. But our first question about Renyi entropy rate is that is the same thing true for Renyi entropy rate? It means that does this limit always exists for stationary processes? And the second question we care about is that because you already seen from the previous slide that the Renyi entropy is a special case, is a generalization of the Shannon entropy. Now, next question is that whether this is true for the Renyi entropy rate, in the sense that is it true that the Shannon entropy, the Renyi entropy rate always converges to the Shannon entropy rate when alpha equals to 1, when alpha approaches 1. So basically, we will focus on these two very basic properties of the Renyi entropy rate. Now, let me talk about some existing results. So the existence of Renyi entropy rate is proved for some special cases. So for IID, it is trivial. And the most interesting part is the so-called Markov case. Basically means that you have a stationary ergodic Markov chain, then not only the Renyi entropy rate exists, but it has a very clean expression. It is expressed by the log of lambda. Lambda is the largest positive eigenvalue of the transition matrix of the random process, but you take entry-wise alpha power. I mean, you take entry-wise, you take the alpha power, and then you obtain a new matrix, and lambda will be the largest eigenvalue of this new matrix, and then normalized by 1 minus alpha. So as I said before, it contains ID process as a special case. And moreover, it has been shown, it can also be shown that for the so-called weakly mixing process, you can also prove the convergence of the Renyi entropy rate. Basically, because in that case, you can prove the subjectivity of the Renyi entropy, I mean, of this term here divided by n when you have weakly mixing. But there's no clean solution. Yeah.
Could you back? This one. So, no, that's convergence theorem. So, I'm slightly confused. No, not this one, not this one. Convergence theorem. Yeah. Of course, I know this one. And also previously you mentioned that some theorem by several persons.
Yeah.
Yes. I'm confused.
Okay.
This is new.
This is what? Can you say it again?
It's 2009, but this result already known many years ago, I think.
Oh, I think the original version appears on 2001. The original version is again by the 3 authors, but it may appear on some conference, which takes place on 2001.
But I think then Daltoni's textbook already explained this one.
Okay.
Daltoni's textbook. This was published many years ago.
Okay. Maybe I should give the most original reference here. Okay. Should I continue? Okay. And our focus in this section will be on a special class of process satisfying the 2 properties. The first one is the boundless property, in the sense that for any realization sequence and any n, the conditional probability is lower bounded and upper bounded. And the second condition is the exponential forgetting. So basically means that if you look at the conditional probability of alpha's power, and you look at 2 different sequences of two lengths, of different lengths. The first one is of length m, and second one is of length m hat. The memory here can be shorter than the memory here, but as long as the memory are the same up to m's position, then the difference of these 2 conditional probabilities will be exponentially close. And as I mentioned before, the reason we're interested in process satisfying these 2 properties, because hidden Markov chain with the mild assumption will, under mild assumptions, the hidden Markov chain will satisfy these two properties. So all our results will apply to hidden Markov process with mild assumption. And the mild assumption here basically means that we have a positive channel transition matrix, and the underlying Markov chain is aperiodic and irreducible, which are very reasonable conditions. And our first result is that whenever you have a stationary random process satisfying these 2 conditions, then the Renyi entropy rate always exists. And we can give a very explicit convergence rate, which is a polynomial form. Okay, so here is the idea of the proof is to use the so-called modified Bernstein blocking method. So this method basically is very useful in considering deal with very complicated probability sequences. So basically, if you want to evaluate this term, which is in the expression of the Renyi entropy rate, then we first write this probability as a multiplication of a lot of conditional terms. So we first write them as the product of some terms, and all the terms here are conditional probabilities. Then in each of the blocks here, we remove the cassis. Then we can do some evaluations using our properties. And then for the remaining two terms, we combine them by cutting down the memory. So we consider the truncated version of these two terms. And then at last, we manually add another term, another conditional term to recombine the whole partition small blocks. And then by this kind of technique, we will get a relationship between the sum of the probabilities here and the sum of the probabilities here, but the length of the sequence will be reduced from n to some power lambda. And whenever we have this kind of evaluation, this expression divided by n and 1 minus alpha basically will give you the average version of the Renyi entropy rate. Then you just take the limit and you can compare them.
I lost your story. So what do you want to prove? Could you explain the statement to be proved?
So we want to prove that this average version of the Renyi entropy rate has a limit. First of all, this is what you can tell from this expression. Means that we first want to prove the existence of the Renyi entropy rate, and furthermore, we want to evaluate this convergence rate. So basically, we have to prove the limit of this term exists. That's the reason we look at the sum of the probability term. Because for this term, if you take a log and you divide it by n and 1 minus alpha, and you take limit, exactly you get the definition of the Renyi entropy rate, right? Okay. So whenever we have the relationship here divided by n and 1 minus alpha, we will have the relationship of the finite of the average version of the Renyi entropy of length n and length n to the power lambda. Then we have this kind of evaluation. The difference of them is exponential. So we can prove that this sequence indeed is a Cauchy sequence. So by the way, this H alpha of n is just the same as the term here. So we can prove that this sequence is a Cauchy sequence, so it always converges. So the limit must exist. And moreover, because here we have a polynomial convergence rate, so basically by doing typical limit argument, we also have the polynomial convergence rate of the Renyi entropy rate. So this is what we want to prove. Okay. So in particular, here in our first result, we show the existence of the Renyi entropy rate for the class of random processes, and also we have a convergence rate. And then the next step is maybe let me first give some remarks on our first result. The first one is that we view the Renyi entropy rate as the limit of the finite block version. And the second is that if you want to really compute the Renyi entropy rate of this given process, then this is not very helpful in the sense that the computation of this term will take is very complicated. It will take you exponential time. And the polynomial convergence rate is not fast enough. So we want to have a better convergence rate. And motivated by the result of the Markov of the Renyi entropy rate of Markov chain, just have this very clean expression. So we want to use the Markov approximation to approximate the original random process and see whether there is a relationship between the Renyi entropy rate of the Markov approximation sequence and the Renyi entropy rate of the original sequence. So let me first give you the definition of the Markov approximation of a random process. So basically, if you have a random process Z, you will have a finite dimensional distribution. Then we define the nth order Markov approximation to the original sequence as it has the same n+1 dimensional distribution of the original sequence, you first have n+1 dimensional distribution, and then you construct the sequence as a Markov chain. That is how you approximate the original sequence by a fixed order of Markov chain. Then for a fixed sequence, you will have a sequence of Markov chains to approximate it. Now, what we want to show is that we want to show that the Renyi entropy rate of the Markov approximating sequence will converge to the Renyi entropy rate of the original sequence. And because the Renyi entropy rate of Markov chain has this kind of expression, in order to prove the convergence here, we want to prove the convergence of this term. So basically, we want to prove some convergence of the eigenvalues between two different matrices. But the nth order Markov chain has a transition matrix, and the n+1 order Markov chain has another transition matrix. These two transition matrices have different scale. So the first thing we do, we will upscale the nth order, the transition matrix of the nth order Markov chain to have the same dimension as the transition matrix of the n+1 dimension Markov chain. Then you can compare these two matrices with the same dimension, and by evaluating the how close your entries are, you can evaluate the difference between your eigenvalues. So for example, the second order Markov chain with alpha 2 has the 2 by 2 is of scale 2 by 2, and the third order Markov chain is of course larger, is the 2 to the power 3 by 2 to the power 3. If you want to compare the lattice eigenvalue of these two matrices, you can first regard the second order Markov chain as a third order Markov chain, and then you can express the matrix here to be a new matrix that has the same scale of this one. Then you can compare the eigenvalues. And the entries here is just the conditional probability with memory 2. Here is conditional probability of memory 3. So the only difference between them is that their memory is of different lengths. But remember that we consider processes with exponential forgetting property, in the sense that when the memories have different lengths, but the first n bits are the same, then they are exponentially close. So basically, after you upscale the matrix here, it will have the same form as this matrix, and those two matrices, the corresponding entries will be very close, in the sense that they will be indeed exponentially close. So you have two very close matrices, then you want to, then the lattice eigenvalue is continuous with respect to the entries. So you will expect that the difference of the lattice eigenvalue will be exponentially small, and this indeed is true. So by doing this, you can get our second main result, which says that under some conditions of the constant in our assumption, then the Renyi entropy rate of the Markov approximation will converge exponentially to the Renyi entropy rate of the original process. And why this is useful? Because in practice, we have a faster convergence rate. Basically, we have an exponential convergence, which is much faster than the polynomial convergence rate. So it may be useful in practice. Yeah, so here, I think I already mentioned the note here. It is exponential, and we use a new sequence to approximate the original sequence. And also, the third point here to justify that this condition is not very strong, in the sense that a lot of channels in practice will satisfy this condition. So for example, the binary symmetric channel with very small crossover probability will satisfy this condition. So this result should be very useful in practice. Okay, so this is the first part of my talk. Is about the Renyi entropy rate. And now let's move to the second part, which cares about the continuity of the Renyi entropy rate. So in this section, in the second section, we will show that the Renyi entropy rate may not converge to the Shannon entropy rate as alpha approaches 1. So first of all, if we don't have a limit version, we consider the finite block Renyi entropy. It always converges to the Shannon entropy. And for all the examples, such that the Renyi entropy rate is known to exist, it always converted to 1. So for example, for ID process, for Markov process, we have just seen before, and also weakly mixing process, we can all these cases have been shown that the Renyi entropy rate exists, and they always converted to the Shannon entropy rate as alpha approaches 1. So we may have the following question: is this true in general? In the sense that, is it true that for all ergodic processes, the Renyi entropy rate always approaches the Shannon entropy rate as alpha approaches 1? And in this section, we will show that this is not true in general. So basically, we want to construct an ergodic process such that the Renyi entropy rate exists, but it doesn't convert to the Shannon entropy rate. So this is our main result in this section. So we show that there is an ergodic process mu such that the Renyi entropy rate exists for order alpha bigger than 1. And when alpha is bigger than 1, the Renyi entropy rate indeed equals to 0. But at the same time, we can show that its Shannon entropy rate is away from 0 in the sense that it is bigger than 1/2. And indeed, this 1/2 can be replaced by some other constant between 0 and 1. And 2 and 3 will imply that when alpha approaches 1 from the positive side, the Renyi entropy rate will not equal to the Shannon entropy rate. Okay, so our idea of the construction is that we want, in order to, so 2 and 3 are the two most important properties in our, we want to have for our process. So for the first one, if we want to show that the Renyi entropy rate equals to 0, basically we want to have some realization sequence to have a probability such that this probability will be approximately larger than exponential, in the sense that the probability of the sequence is bigger than or equal to some beta of m, and this beta of m, if you take log and you normalize it by 1/m, it will equal to 0. So it goes to 0 relatively faster instead of exponential convergence rate. And this will imply that H alpha of mu equals to 0. I will show the detail later. And secondly, if you want to have a random process whose entropy is relatively large, so intuitively, we want to have the process such that is almost uniformly distributed, because uniform distribution always gives you the largest entropy. So if we can show that our process is not very far from uniform distribution, then intuitively we can show that the entropy of that process will be not close to 0, so it will be bigger than or equal to some constant. So these two are the two goals we want to have for our target process. And the way of constructing a process to specify these two conditions is the so-called cutting and stacking method. And this method indeed is from the ergodic theory. And it is very useful in constructing stationary processes when you want to control some probabilities. And some applications of this method, although both of them from ergodic theory. The first one is the Austin used this method to prove the celebrated Austin's isomorphism theorem for Bernoulli shifts. Basically shows there that when Bernoulli shifts, two Bernoulli shifts have the same topological entropy, then they're isomorphic. And Paul Shields also used this method to construct various interesting counterexamples. So one of these examples is that he used this method to show that there exists two ergodic processes such that their divergence rate equal to 0, but they are different. Now, to understand this method, let me first introduce how to have a stationary process in ergodic theory. So basically, in ergodic theory, a process is given by a sample space and a partition and a transformation. Whenever you have a partition of the sample space and the transformation, then you can define your process by x of n evaluated at some sample point equals to a. Whenever this n-1 transformation of the sample point is in the partition P of A. So basically, how we define the process is we look at the location of the sample point here. Now, the cutting and stacking method, roughly speaking, is that we want to express the sample space as a collection of labeled columns. And then this labeled columns will give you a partition of the sample space. Then we try to define a natural map on this gadget. So from downward to upward, you have a mapping. But this mapping is not well defined on the top level of the gadget. So it's not defined almost everywhere. So we want to extend it such that it is defined almost everywhere. And the way to extend it is the so-called cutting and stacking method. And finally, you have the partition, you have a map which is defined almost everywhere, then you can define random process. So here is an example. So suppose now this is, all the levels here, the uni is our sample space. And then we express it in a sequence of labeled columns. So here we have three, in the first column, we have three layers that are labeled by 1, 1, 1, and second one is 0, 1, and then 1, 1, 1, and 0. Now we can cut each of the columns and then stack them together. So this red part will be maintained here, but we cut them from 2 columns to 4 columns. And then we want to move this second, the columns in blue to glue them together with the red one so that we get a new gadget and it is thinner and it's taller. So by doing this, the benefit of doing this is on this expression, the T is not defined on the top level here and here. But if you glue them together, then your T this time will be defined on some of the points here, and previously it's not well defined. So by doing in this way, we can extend our map. So basically, we extend the upper map and the width of the gadget decrease and the height of the height of the gadget increase. And then since every point here is a sample point, by read the labels of the sequence omega, t omega, t square omega, t cube omega, then you will have every sample point will give you a realization sequence of the process. Yeah, so basically here is how it goes, and because I don't have enough time, so I just skip it. And here is the important thing that we can cut and stack the gadget arbitrarily as long as whenever you want to glue two columns together, they have the same weight. Otherwise, you cannot glue them together. So basically, you have a lot of freedom in doing this. And depending on how you carry out the cutting and stacking, you may get a process with various properties. So yeah, here is our construction. So remember that we want to have a process such that the probability of 1 is relatively large. So basically, in our construction, we want to have 2 parts. Left part is a sequence of all labeled by 1. Okay, sure. So we want to have left-hand side to have labels all 1 so that the probability of that part will correspond to the probability of the all 1 sequence in the final process. And on the right-hand side, we want the right-hand side, the remaining part to be almost uniform in the sense that it contains all the possible binary sequences and they have the same measure. And then we can cut and stack to get a new gadget. And by doing this, we can always control the gadget on the left-hand side to have a fixed measure. So for any n, we will have a new gadget S of n, which is contained with which contains Lm and Rm, and L of m always has a fixed measure. So eventually we have a sequence of gadgets such that the left-hand side has a fixed measure and the right-hand side is almost uniform. So these 2 properties will imply that our final process has all 1 sequence have a probability bigger than or equal to beta of n, and this will imply that if you consider the Renyi entropy range, you have this kind of inequality, which shows that the lim sup of the Renyi entropy range will be 0. And on the other hand, since it is almost uniform on most of the sample space, so the Shannon entropy will always be away from 0. So in particular, we will have that the Shannon Renyi entropy range will not convert it to Shannon entropy range as alpha approaches 1. So basically, we finish the construction. Yeah, thank you. That's all about my talk. Thanks.
So is there any question or comment? Could you show me the definition of ergodic process?
Yes. Any questions?
I'm asking a definition of ergodic process.
Okay. Sorry, I can't hear you clearly. Something wrong with the internet.
Definition of ergodic process.
Okay. Here. Definition of the ergodic process. So, okay, so basically, ergodic process means that if you, yeah. So ergodic basically means that if you look at any set in the algebra.
This is the definition of ergodic process. Definition.
How important is stationarity?
I'm asking a definition.
Oh, sorry. Can type it in the chat so that I can read it? Because it seems that your sound is not very clear to me.
Hi, he's asking you to state the definition of an ergodic process, and if you could go to the
okay.
slide.
Sure.
We have that.
Sure. I should give the definition of ergodic process here. So basically, ergodic means that if you of course the process is defined on a sample space, on probability space, right? So if you look at any, maybe let me look at this page. Yeah, here. So in ergodic theory, a process is viewed as you first have a sample space and you have partition and transformation. So basically, you have a transformation for all the sets in the algebra. So the process is ergodic if and only if this transformation is ergodic. And the definition of this transformation is ergodic. Basically means that if you look at any set in this S, its inverse image under T will be the same as itself if and only if the measure of this set equals to 0 or 1. So that basically means that if you want to shift your process, then you will go through all the possibilities of the realization sequence. Yeah. And by the way, ergodicity is very important in proving this.
No, wait, I cannot understand the definition.
Okay. So in ergodic theory, a random process is given by the partition and the transformation, right? So as long as you have a partition and the transformation, you will have a random process, right? And in this case,
this is not the definition, I think.
Of course, you can have various definitions, one from probability theory and another from this ergodic point of view, but I think they are equivalent. So here I'm stating the definition from ergodic theory.
Huh? I'm asking a definition of ergodic process. So this is
Yeah. So any process can be viewed in this way, right? I mean, any ergodic process can be associated with a partition and a transformation, right? And the process is ergodic if and only if this transformation is ergodic. So as long as I can give a definition of the ergodic transformation, then I can use it to define the ergodicity of the random process, right? So this transformation is ergodic if you look at any event in the sigma algebra, the pre-image is the same as itself, if and only if the measure of that event is 0 or 1. Clear?
No. But we don't have enough time. So thank you
Okay.
very much. So sorry, we need
Okay.
to proceed to the next stop. So thank you very much.
Okay. So let me stop sharing. Thanks.